Right. So we have covered, so briefly overview what we have last time. We learned about the convolution. And try to find out how to find convolution of sum for discrete signal and convolution integral for continuous time. Both of them given as a star mark between them. And then the concept is basically the same. We apply the input. We have two signals. One signal is an input signal. The other one is a system response. We have one of them changed to k, one of them changed to n minus k, or tau, t to tau, and t minus tau, and integrate or sum from minus infinite to infinite. So basic concept is pretty similar. To find out the value, we reversed one of the signal and shifted from the lowest case to upper case and see that we have any overlaps to see it. And then we briefly, we have several characteristics of a convolution, and then show how the box, how the system can be representative, can represent the convolution. Basically what we talked before here is, also linear time system is memory, basically memory system, except a very exceptional case that the transfer function is always 0. To find in linear time invariant system to be invertible, we have to find a special function h1 or h1 make a convolution to be delta. When we have a derivation for it before. Also causality-wise, causality is the depending only on past and present. If, as the system response will be reversed normally to be n minus k or tau minus t minus tau, so to be causal, they should be 0 for smaller than 0 case. Also, finally, we talk about the stability. To determine stability, there are several methods we are doing. We will learn a little bit about it in Fourier series also. However, one way we can define a stability is if there is bounded input, bounded output, then it is considered to be stable, meaning that if the input is bounded, b is a constant value, which is this x, the maximum and minimum is bounded. When y is bounded, then this one is considered to be stable. To meet that, we have to make this one to be 0, below infinite. Now, this is a kind of repeating system. However, let's see how what happens if the input is unit function. We have a description that, do you remember, in case of discrete time, the unit system is 1 from 0. And delta function, this is unit system, unit signal. This is delta. What is the relationship between them? Chapter 1, we learn about it, right? So remember that each of the stem is a time-shifted version of delta, right? So this one can be represented as what? Right. Basically, in numerical, in vocabulary-wise, it is called as sum of time-shifted version of delta, right? So we mentioned that this is what? Time-shifted version of delta, right? So we have learned that when this one is input, the output is what? When this delta is the input, output is what? Output is H. Because if you shift, when you put this one to a system and do the convolution to find the output value, this one, when this one do the convolution, this one works as like this. They are time shifted version at each point, and they pick up each point of the system itself. Therefore, the output comes as the system itself. So this is how system response comes in. What if we put unit function and see what is the output? Note that this is a linear time invariant system. So in basic principle, basic idea we try to solve in here is we utilize this, right? So we can consider this one as delta n plus delta n minus 1 plus delta n minus 2, blah, 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 until they have an infinite number. So what you can do, consider them is, here is, what is the output of delta n? That's Hn, right? Right? Note that this is time invariant and linear system, right? So let's use time invariant characteristic. Time invariant is what? If the input shift by time, output also shift by time, but does not change by time, right? So what if you apply the input as delta n minus 1? This one is, right, this one is time shifted version of this. So we expect that output will be same, but somehow time shifted version of H, right? Let's say what's the A1 in this case. We don't know what's A. What about this? We have time of 2, so we have another one has a time shifted version of this. And also, if you apply the characteristic of linearity is what? If they add it, you can separate them into pieces and add it. So if the output response of this one is this, so basically we have an addition in here, so we can add them together. So we can consider unit step like this. That's the basic idea coming here. So let's organize it a little bit. That's one way we can see it. And we know that this one will be 1, 2, 3. But let's talk about that later. Let's formulate the system like we have input of U, output of something. Let's try to use convolution. So basic concept is like that, but we try to import convolution because convolution is general term describing the input and output. So what will be the expected output? That's Ym. Let's say Sn. We have convolution of input H, convolution system, response H, and input of unit function. Mathematically, we can describe them like, because this is a convolution, we will have we pick this one, change n to k, pick this one, change n to n minus k. That's how we do the convolution, right? From here, what you can see? This one is what? If you draw it, this one will be the system response, but reversed in time and shifted by n, right? So in K, they are reversed and shifted by n. That's how it goes. If you multiply any h with this, what happens? They are 0 in larger than n. From n plus 1, they are 0. So we don't need to worry about it. So how we do it? And below 0, they are 1. So we can simply erase this and change this one to n. Right? Make sense? So that's how things are here. They are describing like that. Similarly, so if they ask you what is the step response, just ask is step response, right? Step response. If you are asked what is Sn minus 1, the output shifted by n minus 1, what is it? What is it? When system is H, we have, so this is a case that they are shifted, but shifted by n minus k, right? So we can consider them. Now we are adding from minus infinite to n minus 1, right? So if we subtract them, what happens? If you say Sn minus 1, what happens? Only Hn, right? Hn is what? The system response itself. I'm sorry, there's typo. This is H. This H. So we can find two things. First, to find the output of unit input, step input. So when you remember, it's about maybe 1 or 2 years ago, when you remember you learned about basic calculus or engineering mathematics, when you think about the system response, you have a lot of solution that when there is an impulse input, what happens to the output, what will be time delay, those kind of things, right? No. So when you remember, when you are given as a homework or exam, say that here is a system, they have a delay tau, a value of some value, say that if tau is bigger, they will be delayed more. If tau is short, they will be shorter. But when there is input, what happens to the output? Those are very common problem set to understand the system. Because when you think about the system and you think about the output of the system, you always have to stimulate. You always have to give an input to the system to activate the system, right? For example, this one, this is stable, nothing comes in, so no meaning for us. Of course, you can see it, but doesn't have a meaning for us. This one became meaningful, to be meaningful to us when you give a stimulus, and then there's a response coming out of it. One of the general response or input we can give is impulse. Step, because we will either hit it, this impulse, or we give an input like this. That's how we typically and generally give an input to a system. What is it? There will be either impulse or step input. Step input, we can view them as time-shifted version of unit function. That's the reason we keep on talking about impulse response with delta function and step response, which is coming from unit function. So those two are very representative in our case. We can find two things in here. Let's go back to here. First, to find the step response. So there's a step because it's step, right? Response. We do the convolution of input as unit function. However, how we viewed, we just simply add the system response, which is coming from the impulse from -infinity to n. And they go back to the idea that we have a similar discussion. This unit function is given as a summation, time-shifted summation of the delta. And output of the system from one delta is just h. So we can think that in linear time invariant system, we can view the output of this step or unit input, say that they can be considered to be a summation of individual input coming from time-shifted version of the delta. So if you apply time-shifted version of delta, then you can see in here there's time-shifted version of delta, right? And then because this is summation of the input, u is summation of delta, time-shifted version of delta, we add them together. So physically, they also make sense. In vice versa, we have discussed that this delta is what? This delta is this one minus this one minus can be this, right? So in here, we discussed that this is this, right? Just before. So likewise, you can always view them the same relationship between input and output. I mentioned this more than 10 times in this lecture. Please do not check the video. I don't remember, but more than 10 times, hopefully. I keep on saying that there's a system, what's the input, what's the output. When input is delta, output is the system response, which is the system itself. When input is some x, together output, we go to the convolution of the input and the system, right? We keep on talking about that. And now, to get another general form of the system input, which is unit function, we can view them as not consider, we now consider only the system itself. This H is system itself. We don't care about the input. If we know the system itself, we can calculate the output and the input is unit function without giving the input. And you can find the system response. If you cannot apply delta, what you can do, you apply one step and second step with time-shifted version of two things. Get the one value, one output, get the second output with time-shifted version, subtract that to find the system itself. So this is my I think. But we keep talk about H. If you know H, you can understand the system. If you know to find H, several ways you can do it. You apply delta. If you cannot apply delta, you can apply a step response and then do the subtraction. That's another way you can do it. Likewise, when you have a continuous time, what happens in the continuous time? The relationship between discrete and continuous time, the difference is what? First, this n square bracket change to t round bracket, and then summation change to integration, right? So we simply can understand that, okay, they can be looks like that. That's exactly how you see in here, from the minus delta to t. If you consider this, when this one goes to time domain, minus is what? Differentiation in continuous time. So you can consider them, okay, they will be viewed like something like this, which is exactly what you see here. Oh, the other way, I'm sorry. So this one will be, the subtraction would change to differentiation. So they will be considered to be like this, which is, that's what this slide shows. Questions?
여기서요. 얘가 얘라서 얘를 n-1을 넣으면 n-1를 바뀌는 거라고 이해하면은 이게 바로 이해가 되는데요.
네.
여기서 이 식에다가 만약 n-1을 넣는다고 생각하면
네.
n-1을 컨볼루션 h n-1이라고 생각하면 이게 안 나오고 이게 다르게 나오고
보세요. 네.
n-hk가 n-2가 돼요.
자, 그걸 끝나고 얘기해 줄게요. 네. So question was, well, 되게, What? Okay, saved. 그거 되게 좋은 질문이에요. 그거 이따 얘기해 줄게요. So question was, we view this one, in here we view this one as n, Sn to be n, and Sn minus n to be n minus n. That's very intuitively right. But the question was, what if we directly calculate Sn minus 1 from here? Is it really happens? That's the question. So they need some derivation, so I will cover it after the class. Other questions? Nope. So let's find some application of using this system. So if you're given as constant coefficient differential equation, well, it sounds like a very long equation, but you will see that they will be pretty straightforward. So this example is like this. Example is like this. When you're given like this, dy dt plus 2y equals xt. This is a system, right? What is the output when this is the input? When xt equals ke exponential how much? 3t. What is the output? That's the question. So what is your intuition says? When you're given a problem like that, what will be the first thing you would like to try? Let me change this to here. Of course, the solution is given at the bottom, but don't look at it. So you will see that, okay, and you see the differential y, maybe I will try like this. Right? You intuitively think that you want to do that, right? Why? This S is what we're starting from beginning, say that J omega is Fourier transform, S is Laplace transform. So you already know chapter 9, right? And how do we put the input? How do we put the input? So typically, by far, I think most of the problem you confronted before is that try to find the system response, right? And how we do it after that? You put S plus 2 in the beginning, Y, X, switch, and this is our system response. We already know how to do it, right? And the question now here is, what is Y instead of H? This is H, right? What is Y? That's the question. So to find it, we have to find out Y, right? To get Y, how we do it? We need X. How do you find X? This is time domain signal. We change this one to somehow change this one to some frequency domain signal, multiply, and then find Y. Right? We will learn that in chapter 9. Let's do something more effort needed, more time consuming things. Do I talk too much about ignoring these time domain signals? However, this time domain signal is very important because intuitively thinking, when you see from a real instrument, is time domain. If you have to do some signal processing to see the frequency response. So this time domain signal is more intuitive to human beings. So to solve it, let's go back to first slide. This one is called constant coefficient and linear differential equation. If you remember engineering mathematics, you may remember homogeneous solution versus particular solution. What is the solution? Homogeneous solution for this. What is particular solution? Solution for that. Meaning that you remember that you have one solution YH, second solution YP, right? And then you finally add them together to find output. Why? What's the physical meaning of this? Anybody remember? Proposition, yeah, right. That's one way you can explain it. What about other way we can explain it? Linear, right. Linear is also right. So you can view them in this way. If you have a Y, if you have a solution of this equation, you can have, how to say, you should find out some Y that satisfies all the cases, right? The cases. However, sometimes you can find one solution that satisfies a case, but that may not be only solution. Do you understand the difference? This one may have only one solution, but you can solve it analytically to find the solution, or you guess one solution, put it to here, and see if you can find it. It's similar to our process to check the invertivity. Invertivity, if you remember invertivity, to find it, we don't do many calculation different from other cases. We don't do many analytical process. We just guess one example of H1 to satisfy this equation, and then this one will be invertible. This one is similar to like that. The homogeneous solution is general term. We analytically calculate from the equation. Particular solution, we guess one solution that, so we coming from this H, we come from here, this H, we come from there. We guess one solution, put it to here, and see if they satisfies. That's how we think the difference. So, Of course, the best way you can find is finding a general solution like this, all of this. However, if you don't do the frequency domain change, this one is sometimes tedious. We have to do it. So we try to simplify using the superposition linearity. We try to simplify the system. How we do it? We make the right term to be 0, and try to find one solution. That's a homogeneous solution. And then we guess solution may satisfy this, put it there and see if they satisfy this particular solution. Right? You may ask why we just do the particular solution. Because particular solution, we know that they satisfy it. The answer is like that. Particular solution may not be a general term, may not. Because we guess, without solving analytically, we guess what will be one example solution and put it there and see if it satisfies. There may be more than that, more than one solution. Right? Example is like this. You have this kind of waves and see that find the solution that those two lines are equal. There will be more than one solution. This particular solution we guess. This is just an example, okay? This doesn't have any relationship with the problem. We guess one example, then put it there and find a particular solution. This particular solution. That's the reason that it's called particular. Homogeneous solution, we compare them and see we can find solution for all the points. However, as we are not solving the exact equation but solving something different to simplify the process to find the solution. That's the reason we have two kind of terms. If you have a particular solution, we know that this is a real solution for this. However, there may be more than it. In homogeneous equation, we know that there are general terms for all the cases. However, the equation is different. So we consider them as a system which is 0, system equals x1 as input, and then find a solution for this case plus solution for this. That's how we find it. So let's have those things. First, homogeneous solution. Let's do this. What is the solution for that? There will be exponential 2t times a minus maybe. Okay, that's minus. What is the solution for this? Let's guess one particular solution. In particular solution, what we said, we guess one solution. Say this one is what? Y exponential st, and what is x3? K exponential 3t u t. Okay? If you put this one to here, what happens? First one, if you differentiate the y, that's what you guessed, s, y, s, e, s, t. That's what happens. Second one, 2 times y, e, s, t. That is what? K times e, 3t, unit function. How we find it? Y, s plus 2y times e, s, t. And compare that, this will be the same. So s will be 3. and this should be k. It should be same. So k should be y times s plus 2, right? So y times 5. So therefore, y will be k divided by 5. So our particular solution will be 5 over k and 3. And then we add them together to find the solution. Now, what do we need? So solution is like this. Solution will be this one plus this. You can see them in two ways. First, as I said, homogeneous equation, we started from the original equation, analytically follows to find the solution. How we do it? This is what? Equals 0. To do it, there will be minus 2, right? We know that from the difference equation, we know that the solution will be like this. Of course, we have to add, we don't know about the amplitude. So this A is, we don't know it. We don't know it. So this one, the H, we're starting from the equation, follow the step, and find the solution in analytical way. In particular, solution is what? We guess Y has a form of what over B times EST, for example. We guess output has a form like that, put it to the equation and find what is A and S. So we're starting from our guess and go to the equation. So the way we find it is quite different. With this one we find, that's the reason the output, even though we find a similar Y, this one is minus 2, this one is 3. But we don't know one more thing. We don't know what is A. So we have to know initial condition or auxiliary condition, which is initial condition. Initial condition, it has a meaning that the response at time of 0, right? Auxiliary condition has more general meaning, I think. It's a more general meaning, say that it's a value at any point. Don't have to be value at 0. But if you have one example at one point, you can put it there and find A, because we already know the system. When you confront nth order solution, any questions? Questions by far? Before we move on. Nope. All right. This is a first order differential equation, right? We differentiate only one time. If you consider multiple differential equations, say this one is, you can consider them like that. You can consider them like, if you confront so on, you may have this kind of differential equation also, right? This is called nth order equation, what is seen here. So when you see this in here, this one means that they have differentiate first differentiation, second differentiation, third differentiation until nth order. In x, likewise, we differentiate from one differentiation, zero differentiation, which is same with the x, until m differentiation. This is the general term we will see in differential equation. How do you find it? Similarly, we do the same thing. How we do it? First, we first find out the homogeneous equation. Make the right term, which consists of x, make this one 0, and find the homogeneous equation. And second is what? Then we need a particular solution. So we put on arbitrary x, we put arbitrary y, it is fine the input x. Similarly what we did before. Of course, this one has the same concept to solve it, except this one needs much more calculation. For example, in our first example, the first example we had before, we relatively easily find what is homogeneous equation, what is a particular solution, right? This one has more terms, so we need more effort and more guessing to find homogeneous and particular solutions. That's the only difference. Once again, ask your intuition what you want to do. There's one way you can do it. However, what you can do it here is 2s 3s squared 4s 3 times y equals 1 2s 5s squared and x. This one is looks easier compared to you put y in the solution right away. So that's the reason we talk about it. Talk about the Laplace transform or Fourier transform. Likewise, this is continuous time. In discrete time, this one I feel a little bit uncomfortable because you can view them in this way. If you want to change this one to discrete time, there will be which is the differentiation plus 2yn equals xn. So looks a little bit unfamiliar, right? But sometimes you confront this one in discrete time. Likewise, we have additional y, and additional x, and try to find solution. Likewise, we put them as homogeneous and particular solution, find each of it, and assume the initial condition, and we find a solution. So it's quite similar looking things. However, it's more, how to say, it will be more, sometimes much easier if you do Inveriant in time domain, not time domain. It's much easier when you do in frequency domain. So, let's think about how to use a system model to represent this differential equation. First, So now we switch our mode and think about some drawing lecture. If you are given a differential equation, let's bring in discrete time first. So that's a little bit more intuitive in this case. Let's bring in that you want to find a system response of yn plus a y m minus 1 equals x n. If you are given that, if you are given that, you want to draw a picture representing this differential equation. How we do it? Of course, the answer is given like that, right? So when we talk about drawing the box, we talk about drawing the schematic. I give you one advice that we first select what is the input, what is the output. If you remember the circuit example we had before, remember we try to have what is the input, what is the output. Let's clarify it. What's the input, what's the output, and put a box. Actually, you don't have to draw a box, but let's see. So what's the input? X, right? What's the output? Y. And what is the relationship between X and Y? So X is coming, Y will come out. So let's reorganize this equation, because we want to find the output, we want to have a form that output equals something instead of output minus some output equals input. So we want to have more familiar form that only output left and move everything to the other side. So okay. So we want to have what? In here, we know that we want to have bxn minus a y m minus 1, right? In here, we want to have it. First one, where can we have it? First one, we have this, right? So we simply extend the line, put a multiplication of the b, and things like that. That's one way you can do it. So you don't have to draw it. You don't have to draw it. I will rephrase it later. So the logic here is, we know that the output y is this, and how we make each of it. And then finally, if you subtract that, then we will find the output. The first sentence, the first one, you have x in here, we extend the line, put a multiplication line, say they multiply by b, and they will be the first part. What will be the second part? We should utilize the output. We take the output, put or if you have a MATLAB, there is a corresponding program called Simulink. If you have a MATLAB, type Simulink. And then there are same company, same program, and another one pops it. MATLAB is basically when you type it, basically graphical, not have many graphical, is command-based. Simulink is more, more block diagram wise. So they actually looks like this. You pick up boxes, one box, they are something called multiplier, one box. Sometimes they call a differentiator, integrator, sometimes delay part. So we pick delay. And then what? This one becomes delay by 1. They will delay by 1. And then you put a multiplier, A, and then they comes in like this. But looks a little bit too much to us. Actually, that's right. That's okay. So let's redraw a little bit to make this one a little bit simpler. We try to erase this minus. To erase this minus, how we do it? Minus is what? When this one goes to this way, coming to the output, then this one will be the minus. If this one, I think it's better to draw again in here. So input that this is x, and this output is y. So still do a black box. The concept still holds that we take out the y and delay it, but we need this. And previously we put them again to here and make a minus, right? Now let's bring it to input. Let's bring it to input. Then the direction changed, so we don't need a minus, right? And then what is here? What is here? There will be time shifted version of this, and you may add a here. So if you put b, you should put it in front, because this one b don't have to be multiplied in here. So we put b in here, put them together, and take it out. So we can basically do similar, but we can remove this one from outside, bring it to the front. That's how this picture shows in here. However, there are several ways you can do it. You can put either minus in here, or you can put minus here. So these two are, so choice number 1 is white. You put it like this, or just put plus and put minus in here to get the output. Of course, this is another choice you can try. But this one shows there's 3 examples already. One system, you can build the system in 3 different examples. Meaning that the claim I had in the beginning of the lecture is still hold. Say that to show a graphical schematic of the system, you have multiple choice. You can make it a little bit differently, a little bit difficultly, or easier if you want. But either one is your choice. Right? What I'm doing now, why I'm showing it here is later chapters, you are asked to draw the system. When it says here, you are given the system, say that draw a schematic representing the system. There's many ways you can do it. My basic advice here is, first, select what is input, what is output. Select in here is straightforward. X is input, Y is output. But you can select X minus N is the input, Y minus 2 is output. Or differentiation of X as output, integration of X as input, differentiation of Y as output. You can have multiple choice, because even though you consider if you consider differentiation of x as an input, integration of y as output, you can always have in something called integrator, you can always have something called differentiator to get y and x. So if this, what I'm saying here is you don't have to always x and y is the input and output. But to fill the box, you don't have to select x and y as input to the box. You can always put something to compensate the input x to x, some form of x, y as some of y. You always can have some boxes to do it. Right? And then you begin to fill the box. To fill the box, you rephrase, reorganize the equation to be y, your output of the box, to be some forms, and see how you can route, how you can wire to get those equations. That's how the logical step goes. Define what's the input and output to your box. Reorganize the equation to be the output of the box equals something, and think how you can wire or route, how you can get this value from some point and organize it. That's how the step goes. So once again, they can be either differential-wise plus multiplication, delay, likewise in time domain plus multiplication, differentiation, and also integration. They may happen. So one more time. These two, we will not cover this one this lecture. However, this is the extended version of that. These two push to self-calculation to draw these two. Actually, these two are representing the same system. So if you put this one, you put x as an input to your box, y as output to your box, from your box, and then make y equals what? Y equals a over 1 times minus dy dt plus bxt. That's one way you can do it. So this one is, we rephrase it. So y equals what? In this route, they should be minus 1 divided by a times differentiation of the y. So to get the differentiation of y, we put multiplication, put it here. Also, right turn, we need a over 2 times x. So we route, add them together to get the y. That's how we represent straightforwardly. This one is actually the same system, but we reorganize a little bit differently. For example, I once told you that the input to your box don't have to be x. They can be integration, delay, any form of it. If you assume now we are trying to have here. We are thinking about here. Now we assume what is dy dt? That is our output. That is our output in this case. To get this, what is it? Minus a yt plus bxt. Right? So this is what second one shows. At this point is dy dt. At this line, at this point is dy dt. To get it, we need the multiplication of x, which is right term in the thing on the board. To get the left one, we need to have minus a times y. We add them together. And then this point is dy dt, differential of y. And then we add integration part to get y. This one looks simpler than this, right? Of course, we don't know. The real system, we don't know. But it looks a bit simpler than that. So we don't need this kind of a bit more looks complicated variables. We only need the a and b. But we never know because integrator is sometimes hard to manufacture. So that's up to your choice. So in short, one more time, define input and output to the box, input and output from the box. We organize accordingly. This side will be output of your box and organize it and see that how we can route to find it. And there will be more than one choices. That will be the final thing of today. Questions? Really? All right. So let's have a taste. Just have a taste of Fourier series today. So by far, we have talked a lot about the system and signal, property, delay, causality, memory, reversible signal. Those are the practice to understand from now. From now, we try to understand how to change, how to modify a given signal to different forms so that we can understand the original signal easier and more straightforward. So I summarized some of it. So we will learn about in chapter 3 Fourier series, chapter 4 and 5 Fourier transform. One is continuous time Fourier transform. Second one is discrete time Fourier transform. And then chapter 9 we have Laplace transform, which is the most general term to use. If you consider what is the difference, why we have to hear the guy's name Fourier so many times, because I will say in two ways. First, we have to learn to understand the different signal. Fourier series is time domain. They still stays in time domain. Most likely, they still stays in time domain. In Fourier series, the assumption here is the signal is periodic. A set of signal is keep on repeating by time. So Fourier series does not satisfy, generally does not satisfy in non-periodic signal. In non-periodic signal, we cannot generally use Fourier series. But in periodic signal, we can use the Fourier series, and we still not touching much in frequency domain. We still stays mostly in time domain. From Fourier transform, so if you see here series, that's still in the time domain. Transform is we're changing, right? So we're changing from time to frequency, frequency to time. So the real frequency time frequency shifting happens from chapter 4, Fourier transform. They are true for periodic signal. They can be applied to non-periodic signal also. That's the reason we have to have both series and transform. However, there are several cases Fourier series doesn't satisfy. In the beginning of the lecture, I showed Euler circle or Euler equation. Say that Fourier series, Fourier transform stays only in the unit circle. Laplace transform, they can cover all the complex plane. So Laplace term is more general term. However, there's limitation. So we will learn about it from next lecture. That's all for today. And questions.